So we learned how to find a gradient from first principles based on nice line segments, but then we've also now found a nice short rule. If we want to differentiate any function of the form x to the n with respect to x, then we bring the power down, we write x, and we reduce the power by 1. So this says differentiate the thing in the brackets with respect to x. That is the same as saying if you have a curve of the form y equals x to the n, then its gradient is given by nx to the n minus 1. Or if you have a function x to the n, then the rate of change of that function with respect to x, f dash x, is equal to nx to the n minus 1. So that's our general rule, and it's really quite powerful. For example, if we are given a fraction, because we can write this fraction as x to the power of something, x to the power of negative 3, then we have a rule that tells us what the gradient is. So the gradient of that curve will be, we bring the power down, negative 3, x, and we reduce the power by 1 to the negative 4, not negative 2. Okay, let's look at another one. So we have 5 over 7x to the 4. Now because we can write that as 5/7 times by x to the negative 4, we can now apply our rule, because this is just a number times by something in the format for our rule. So we'd have the gradient of this curve would be 5/7 times negative 4x to the negative 5. So I'll slightly tidy that up. Negative 20 over 7, x to the negative 5. Also, we can deal with roots. So if we've got, let's have a function this time. We've got f of x is equal to the 5th root of x. Now we know how to write that as a power of x. So we've got x to the 1/5, so now we can apply our rule. So f dashed x, that's the rate of change of x with respect to x, how fast f of x changes when you make a little change in x. We get the power comes down 1/5 x, and we reduce the power by 1, so a 5th take away 1 whole is negative 4/5. Okay, one more example. If we have a function f of x is the square root of 7x cubed. Now because we can write that root as, would have root 7 x to the 3 over 2. Remember flower power, that's the high power, and then underground root, so it's the square root. We can now apply the rule for the derivative. So we bring down the power, so we've got root 7 times 3 over 2 x to the, now 3 over 2 take away 1 is just 1/2, so that's definitely a bit easier. Let's tidy that up slightly. So 7 root 3 over 2 x to the half. Okay, so for all of these, we end up with something in terms of x to the n, and that's absolutely fine. If you're presented with a fraction or a root, it's definitely easy to do algebra with it in this format. But if you're asked to find a gradient or to do differentiation, then it's much easier to write it in the form x to the n. So you write it in the form x to the n, and then you apply the rule that we've learnt. Then at the end, if that's all that's asked of you, just leave it like that once the numbers are tidied up. If instead you are, for example, given a gradient and told that your gradient equals that, and at what point does it equal that? So you're going to solve an equation or find the value of the gradient at a particular point. Then it's easier to turn it back, it's easier to deal with if you turn it back into the fraction or root format. So you'd have negative 3 over x to the 4 for this one. Or for this one, we'd have negative 20 over 7x to the 5. For the next one, we'd have, so 1 over 5, and it's flower power underground roots. So it's going on the bottom because of the negative power. It's the 5th root of x to the 4. And for the last one, we would have 3 root 3 and over 2, and we'd have root x, so I can pop the x inside the square root sign there. Okay, I hope that helps you.